All right, so yeah, we started with a quiz today. And again, I'm trying to do these more often. I just keep forgetting. So there should be another one sometime soon, all right? And I hope you guys are able to do these. Let me just go through the solution right quick. So this one is 2x plus 3 e to the 3x. That's the answer to that one. This one is minus e to the minus x sine of x squared plus 2x e to the minus x cosine of x squared. That's the answer to that one. And this one, I have 1 over 2 times the square root of x plus 3 times 2 to the x rather, plus x squared, and then minus the square root of x plus 3, quantity times natural log of 2 times 2 to the x plus 2x, all divided by 2 to the power x plus x to the power 2 squared. So the first one is additivity, and then the chain rule brings down that 3, right? So any questions about number 1 here?
I thought that E doesn't change.
E doesn't change, but we're differentiating here with respect to x, not 3x. So the chain rule says we're looking at like d dx of e to the u, right, with u equal to 3x. So that's d du of e to the u times d dx of 3x. And then, so this gives us a 3, and this is that e to the 3x. So that's why there's a 3 there. So you got to be careful. Like I said, anytime we're differentiating something where it's a function of something other than the variable we're differentiating with respect to, we got to think about chain rule. So, like this one, what's going on here? This is product rule, right? And the derivative of this one is minus e to the minus x. Why is there a minus there? From the negative x, right? So you might have missed that one too, right? But in some sense, this is good. This means you're consistent, right? In some sense, I'm much more bothered if a student has the 3 here, but then doesn't have the minus here. Like there's a stability to your thinking, which is good. That means you can fix it if you fix it. But the point is, we're differentiating with respect to x, not minus x. So we have to multiply by the derivative of the inside function, which gives us a minus 1 in this case. And then over here, this 2x is coming from, the inside function being x squared. So the derivative of x squared is 2x. The derivative of sine is cosine, right? So this is the product rule, and there's a chain rule to bring out the minus, a chain rule to bring out the 2x on the other term. Yeah. And then here, this one is quotient rule, right? So why wasn't there anything, this is the derivative of the square root function is 1 over twice the square root function, right? Why isn't there like something else multiplying that? Well, here the inside function was what? X plus 3, right? What's the derivative of x plus 3 with respect to x? Well, it's just 1, right? So the chain rule doesn't really do much there. So we have f prime g minus f g prime. Over here, remember we learned the derivative of 2 to the x was natural log of 2 times 2 to the x last time. And then, of course, derivative of x squared is 2x. And then we divide by the denominator squared, and that's that. So, so if you're not like 100% on board yet, that's okay. It's important that we have these little quizzes so that you can kind of see where you're missing something and adjust, right? That's good. So that's why we're doing these. It's not to like assess your, your competence overall in the course, right? It's to help you to try to get closer to the truth. But I hope everybody at least did linearity, the product rule, and the quotient rule from what I saw looking at people's papers. So that's good. I mean, that's half the battle, right? Okay, so what's that? Can't spell, logarithmic differentiation. So logarithmic differentiation is a technique of differentiation we use when it's a pain to do well, there's a couple different reasons. One of the reasons, there are basically two different reasons. Here's the two reasons why. One, we can't do it otherwise. We can't do it the usual way, direct way. And the other reason is log properties make the differentiation much nicer. All right. So I'll start with the first one. All right. So example 1. What if we were going to calculate the derivative with respect to x of x to the sine of, say, x squared? See, we can't just differentiate that because it's not one of the functions that we have, right? Like we know x to the something, right? But that something has to be a constant, right? Our power rule is x to the n, where n is a constant. But n is not a constant here. It's the sine of x squared. So it doesn't fit the pattern of the things we've done. So what we're going to do in this case is give it a name. Call that thing we're trying to differentiate y. All right? Call this y. Then what we have is we have y is equal to x to the sine of x squared, right? And then the technique of logarithmic differentiation basically starts by taking the log of the equation. Take the log, the natural log, in fact. Natural log of y is the natural log of x to the sine of x squared. And what are the key properties of the logarithm? I'll write them up here. One of them is that the natural log of like a to the power p is p times the natural log of a. That's one of the properties of log we love to use. Another one, the natural log of a times b is log a plus log b. And then, of course, we also have log of a over b is log a minus log b. And then beyond that, I suppose there's stuff like natural log of e to the whatever is the whatever, right? Those are the big ones. Want to see a math joke? Yes? Oh, let me finish this before I digress with a math joke here. So which one are we going to use? We can pull this down by property of log, right? The power property. So this is the sine of x squared times the natural log of x, right? All right, so we've got log y equals the sine of x squared times the natural log of x. And now what we can do is we can take the derivative of that. We know how to take the derivative of this, right? And so differentiate Yeah, we got a product rule, we've got a chain rule, a couple different chain rules, right? So on the left-hand side, we have 1 over y times dy dx. On the right-hand side, we differentiate sine of x squared. The derivative of sine of x squared is 2x cosine of x squared times the natural log of x plus the sine of x squared times 1 over x. So I'm using the product rule. This is f, this is g. That term is f prime, this term is g, this is f, this is g prime again. And I'm using the chain rule, right, on y, because natural log of y, well, that's a function of y, not x, right? And on the other side, trying to zoom in here a bit. Okay, so almost done. Now what do we do? What are we trying to find? We're trying to calculate dy dx, right? So solve for dy dx. What do we get? So we get d dx of y, which was x times the sine, x to the sine of x squared, equals to what? Multiplied by y, right? So it's equal to x to the sine of x squared times what I found down here. Yeah, 2x cosine of x squared times the natural log of x plus, I'll write it this way, sine of x squared all divided by x. And there you go. That's how we differentiate something like this. Let me tell you, there's one kind of like this in your homework. So problem 92 is kind of a more complicated version of this problem. But you can do problem 92 in the same way that I did this example, all right? Okay, so that's an example of we can't do it the direct way, all right? Now, the second way, though, example 2, all right? Suppose we had something like the following. We're trying to calculate dy dx when y equals to, let's say, e to the x squared times the square root of 1 plus x cubed times the cosine of 3x. So this would be kind of a pain to differentiate directly, right? We'd have to do a triple product rule, right? Let me show you how this problem looks if we use logarithmic differentiation. So logarithmic differentiation says you take something complicated like this, and you take the natural log of it, all right? Now, what assumption am I making if I take the natural log of something, by the way? There's a string attached here. We can take the natural log of what kind of numbers? Positive numbers, right? So when I take the natural log here, I'm assuming that we're looking at such x that cosine of 3x is positive, just for the sake of this example, all right? But that's actually a good reason to be a little bit cautious about using logarithmic differentiation on this. If you had this kind of example come up in an application, you got to be wary. Is everything involved here positive? If it isn't, I got to think twice about using logarithmic differentiation. Because I could find myself writing nonsensical things, but here we go, natural log of y. All right, so we've got natural log of e to the x squared, right, plus natural log of 1 plus x cubed, and I'm going to write that, instead of square root, I'm going to write it to the 1/2 power, because that's what it is, right, plus the natural log of the cosine of 3x. So what property of logs did I use there? I used the property up here that the log of a product is the sum of the logs. That's still true if you have three things, right? So I guess technically I'm, I mean, if you want to fuss at me, you could and say, well, you didn't really use that one because you had three things, right? Well, if there are three things, you can add a letter here, and it just does that, all right? So why did I do that? Well, I did that because now we can use properties of logs to further simplify things, right? So you guys tell me, what's the natural log of e to the x squared? 1? Well, natural log of e to the Pac-Man is Pac-Man again, right? So here Pac-Man is x squared. So this first term, just x squared. The second term, pull out the half, 1/2 natural log of 1 plus x cubed, right? The third term, I can't really do anything to. I'm just kind of stuck with that. It is what it is, all right? But this is very nice because now we can differentiate the logarithm of y, right? And the advantage there is that what happens when we differentiate a sum? We just differentiate each piece that's being added separately, right? And so 1 over y, dy dx on the left-hand side, because chain rule, right? And then, so I'm differentiating here, okay? Differentiate with respect to x. Yeah, so when we differentiate log y, we have to do chain rule because we're differentiating with respect to x, not y, right? So multiply by dy dx, that's chain rule. So in fact, this is a good, a good observation to make at this point is throughout all of logarithmic differentiation, we keep using the following chain rule. D dx of the natural log of u works out to 1 over u times du dx, right? This is the chain rule for the logarithm, the natural logarithm, right? We actually have not talked about how to differentiate log base 3 of something yet, have we? No. I'll do that next, but let's finish this example first. 1 over y dy dx. So differentiate x to the power 2, that's just derivative of x squared is 2x, right? Then I have plus 1/2, 1 over 1 plus x cubed, right? Times the derivative with respect to x of 1 plus x cubed, right? That's the chain rule there. And the next one, 1 over cosine of 3x times the derivative with respect to x of the cosine of 3x. That's the chain rule, right? And so what do we get? We've got 1 over y dy dx. Well, let me point out here, I'm going to make a slight algebra step. Going from here to here, instead of writing 1 over y on the left-hand side, I'm going to multiply I'm going to multiply this equation by y. And I'm going to say this is y times all of this. Y times whatever's here, right? Multiply this equation by y. So the y gets gone on the left-hand side, right? You can think about cross-multiplying it over to the other side, however you think of it. And so y, right? And so what do I got? I've got 2x plus, well, 3x squared, right? Divided by 2 times 1 plus x cubed. I just brought the half inside the fraction like that. And what's the derivative of cosine of 3x? Negative 3 sine 3x, right? Where'd that 3 come from? The chain rule, right? Just like that problem on the quiz, problem 1 or problem 2, same problem.
So, the problem, 3 is raised.
Yes, but
here, 3 is just laid down. It's the base.
oh no, but in both cases, it's the same pattern. We have some function you know, right? Some function you know f, right? But the formula you're faced with is f of 3x in both cases. It's just either you've got f of x is e to the x, or f of x in this case is cosine of x, right? But you're looking at f of 3x here, and you were looking at f of 3x over there. Whether the 3x appears as an exponent or appears as the argument of cosine, that's just, don't be fooled by the notation. It's really the same pattern. Cosine of 4x, you mean? Yeah. If this had been 4x, then we would have had 1 over cosine 4x here, and we would have had a 4 sine 4x there. And of course, this is actually what? This is actually tangent, isn't it? So we could simplify our answer a little bit and say, aha, well, the answer then is that d dx of, e to the x squared, square root of 1 plus x cubed, cosine of 3x is in fact equal to, well, that quantity again, e to the x squared, square root of 1 plus x cubed, cosine of 3x times quantity 2x plus 3x squared over 2 times 1 plus x cubed minus 3 times the tangent of 3x. And so there you go. This is the technique of logarithmic differentiation. It allows us to take on products of multiple things and break them up into a sum, and because that's the property of logarithm. The logarithm of a product is, a sum of the logs. That's the power. One of the powers of the logarithm. Any questions? Let me look at another example with you guys of logarithmic differentiation. This one will be both easier and more complicated. So example 3. Let's use logarithmic differentiation to calculate let y equal to x minus 1 times x minus 2 squared times x minus 3 cubed plus times x minus n to the n power. So to do this directly in terms of the product rule, it's a pain, right? Because you'd have to use like the n-fold product rule, which is not impossible, right? But logarithmic differentiation makes this problem way, way easier. We take the natural log of y. And what do we get? We get natural log of x minus 1 plus 2 times the natural log of x minus 2 plus 3 times the natural log of x minus 3 plus n times the natural log of x minus n. So I'm using first of all, that the log of a product is the sum of the logs of the factors in the product. And then I'm pulling down the power in each case. Power 2, power 3, all the way to power n. Yeah, the extension of this to n things, but yeah. You know, you could prove by induction that you can extend that to a product of n things. I won't do that to you guys today, but it is true for more things than. And so the beauty in doing that is now when we differentiate that equation, it's very simple, right? The main drag here is that when we differentiate with respect to x, well, derivative of natural log of y, there we got to use chain rule, right? But on the other side, we have derivative of this, right? Plus 2 times the derivative of that, natural log x minus 2, right? Plus 3 times the derivative of the natural log of x minus 3, right? And so forth and so on, until we get n times the derivative of the natural log of x minus n. Now, in some sense, this makes a bad test question because if students don't understand the chain rule, I might not catch them on this problem. See, because the chain rule for all of these is kind of stupid, right? In this case, u equals x minus 1 is the inside function, right? But what's du dx? One. In this one, the inside function is what? X minus 2. What's du dx? It's 1 again. This one, u is equal to x minus 3. Du dx. All right, I'm starting to get bored. U equal to x minus n. What's du dx? 1 again, right? So the chain rule for these functions, it's kind of boring, right? We just do 1 over u for each one of these. And so what we have is we've got 1 over y dy dx equals to 1 over x minus 1 plus 2 over x minus 2 plus 3 over x minus 3 plus n over x minus n. And so here we go. This is the answer. Dy dx is equal to all this stuff times y. What is y, though? Y is x minus 1 times x minus 2 squared times x minus 3 cubed, all the way out to x minus n to the n. There you go. That. So would you, I hope you can see, I hope you would agree with me that using logarithmic differentiation is much preferred over direct differentiation of something like this, right? If you differentiated it directly, you'd have to write out n things, each with n terms. It would be just a colossal mess. Logarithmic differentiation not only made the differentiation process easier, it also simplified our answer. We factored out what you could, in a sense, you know? And you could multiply, if you wanted to, you can multiply this back in here and recover the answer that you would have got through direct differentiation just the same. But so do you guys think you can do logarithmic? I'm going to let you try the homework, and if you have further questions about this technique, you can bring them to me. All right? Future class. One last, I would say that this, to me, this material goes hand in hand with the calculating the derivative of the inverse function, because it's kind of the same method, in a sense. Like you have something you want to differentiate. You can't differentiate it directly, so you do some bit of algebra on it to change it to something you can differentiate. In this case, with logarithmic differentiation, it's just that it's not that you can't differentiate it. It's just that maybe you don't want to. And taking the log, well, it gives you access to the, full tool set of logarithms, which is nice. Okay, so next up, one last example here. Suppose we want to calculate the derivative with respect to x of log base a of x. How would we do that? So we say y equals to log base a of x, right? I think this time, taking the natural log is not going to help us. This is not technically a logarithmic differentiation problem, right? So maybe I shouldn't call this example 4. I should call it something else. I mean, this is something different, all right? But my question is, how can you change that to something that you do know how to differentiate? What happens if we raise, I'll give you guys two choices. We could either do e to the something. Oh, that one's complicated, though. Do you guys know how to rewrite that as a natural log? Do you know the change of base formula? That's my question. Mm-hmm. It's something. I'll get us started. We put natural log of x up here. What do you divide by? Y. It's got to be something involving a, right? But you have to divide by the natural log of a. That's actually the change of base formula. Now, is this a viable method of calculating this derivative? I think I've just shown it's not, right? Because you guys don't remember the change of base formula, right? If you did, then, well, if you know the change of base formula, then this problem is like very easy, right? d dx of log base a of x is what? Differentiate that, you get what? 1 over log of a, which is a constant, d dx of log x, which is what? Derivative of the logarithm is? One over x, right? So the answer is 1 over x times the natural log of a, if you like. That's the derivative here. Now, another way to do this problem, though, would be to take this and raise both sides to the a power. So a to the y is a to the log base a of x, right? So I'm going to show you an argument that doesn't involve the change of base formula, all right? There we go. Then what? A to the log base a of x is x again. what was the derivative of a to the y? We learned that last class, right? So we got d dx of a to the y equals dx dx. And that's what? That's natural log of a times a to the y times dy dx equals to 1. So dy dx is what? 1 over natural log of a times a to the y. What is a to the y equal to, though? A to the y was equal to x, right? A to the y was equal to x. So again, we get the same answer, the natural log of a. I'll write the x out front. So with change of base formula, without change of base formula, But anyway, we can differentiate log based something else. We just have to divide by the log. And why didn't we have this pesky natural log of a thing coming up with the natural log? What happens with natural log? What happens when a is equal to e? Special case, right? Natural log of e is what? the natural log of e is the natural log of e is 1, right? So, yeah. And so that's why we didn't see it before. When we were just differentiating plain natural log, we get 1 over x. So that factor's not there. Just like the other formula, right? d dx of a to the x is what? Natural log of a times a to the x. So in this special case, that factor in front goes away, and you just have d dx of e to the x is equal to e to the x. But base e is a very special base. It's that base where we don't have, the derivative of the function is equal to the function again, right? That makes the exponential a very special function. Okay. So that brings us to our next topic. So the next topic is related rates. All right? So let's look at some examples. So example 1. 2 cars drive away from each other Here's a picture. So let's say car 1 drives due east at 30 miles per hour. All right? And car 2 drives due north at 60 miles per hour. Okay? Then the question is, how fast is the distance between them increasing after 1 hour? Well, let's say 2 hours. Assume both start at the same point. And furthermore, we're going to assume that both are driving at constant speed. All right? Now that's important. These problems, you don't have to give problems, we don't have to give problems that have constant speed, but if we do have constant speed, then we know the relation between distance and time. And like distance is rate times time, right? So the distance is the rate times the time in this case. So what's the distance for 1? 30 miles per hour, right? What was the time in question? 2 hours, right? So times 2, what do we get? We get 60 miles, right? And what's the distance for 2? 120, right? Because we get 60 miles per hour times 2 hours. The hours cancel, leaves us miles. We get, as you said, 120 miles. Okay. Now, I suggest that instead of saying this is D1 and D2, I would say that we should say that this is, I'm going to recommend that we call this X. And we call this Y. But technically, it's X of 2 hours, and this is Y of 2 hours. All right? And furthermore, let me draw the X and the Y back on the picture. All right, so here's X, here's Y, right? And what are we asking? We're asking how fast is the distance between 1 and 2, right? Changing after 2 hours. So what is the distance between 1 and 2? How do we define distance between points in the plane? It's the what? It's the length of the line that connects them, right? So it should be this distance, right? And do you have an answer for me? I'm not really looking for the number. I'm really looking for the distance in terms of X and Y. Let me call the distance between 1 and 2, let me give that a name. Let me call this S. So what is S as a function of X and Y? There's a right triangle here, right? That was east, that was north. So we can look at this right triangle. The hypotenuse is square root of x squared plus y squared, right? So if we want to find how fast ds dt is changing, we can calculate ds dt. This is the calculus here. So ds dt is d dt of that, right? Here x and y are both functions of time. So we got to do a chain rule. And so what we got is we got 1 over 2 times the square root of x squared plus y squared, right? And then times d dt of x squared plus y squared. Remember, both x and y are functions of time. So we still have to do a chain rule again, right? We're going to get 1 over 2 times the square root of x squared plus y squared times 2x dx dt plus 2y dy dt. Now we can figure it out, all right? Because we know everything here, we just have to, this is ds dt at time t. This works for other times other than time equal to 2 hours, right? But at time equals to 2 hours, when we plug in the data that we're given, that's going to give us the answer we're looking for, all right? So when t equals to 2, ds dt at time 2 Notice that we can cancel these factors of 2 out, right? So let's just do that. And we have 1 over the square root. X was 60. So we have 1 over 60 squared. And y was 120 plus 120 squared times parentheses x. What was x? X was 60. What's dx dt? Dx dt is given to us. Dx dt is 30. Dx dt is 30. That's the rate of change of x with respect to time. So dx dt here is 30. Yeah, that's dx dt, 30. And then plus what was y? 120. And what's dy dt? It's given to us. It's 60. And so I need to get my handy dandy calculator and I'll tell you the answer. Hopefully I have a calculator on me. Uh-oh. External hard drive, that's not going to help us. I get 18,000 for the thing inside the square root. So whoa. Oh, my calculator is just, I think I pressed the numbers wrong. Like I got an absurdly large number. I think 67.08 is what we should get here. I'll just keep four numbers. So 67.08. I'm just rounding a little bit. 67.08. And of course, this is in miles per hour because I use miles per hour and miles to. So. Good. Let's see here. Example 2. All right, suppose a clown has a conical balloon. Now, I've never actually seen one of these, but if you could imagine there being such a thing as a conical balloon for the sake of discussion here. In other words, it looks like this. All right, so maybe that's an approximation to a curved shape or something, all right? But suppose you have a conical balloon, and this clown is blowing air into this conical balloon, and blows air at 1 cubic foot per second when the base is at r equal to, let's say, 6 inches and the height of the balloon is, let's say, 12 inches. Well, let's say, fine, 18 inches. At what let's see here. At what rate is R changing if we assume the balloon maintains its shape? As it is inflated. So what I mean to say is, like, the balloon, if we draw it at different stages, when it's really blown up, it might look like this, right? But when it's less blown up, it might look like this. But the thing that will be common is they both have kind of the same angle. Yeah. So in order to make sense of this problem, we need to know what the formula is for the volume of a cone. Do you guys know what that is? The volume of a cone? So here I'm calling this distance r, and this distance from the tip of the cone to that's what I'm calling h. The formula for the volume of a cone, and this is something we can derive with integral calculus a little bit later this semester, is 1/3 pi r squared h. So what is another volume formula you should be aware of besides this? There's another one in your homework that, like, there's a problem like this in the homework, except instead of being a ridiculous conical balloon, it's a spherical balloon. What's the formula for the volume of a sphere of radius r? Do you guys know? What's that?
Is that the area? 4 pi r squared?
4 pi r squared.
3 over 4 pi r squared. Any of those, that's the formula.
Oh no, I forgot to pan the camera over. Well, I did it now, so hopefully they can see everything. Sorry to those of you who are not here. So yeah, now you said 4 pi r squared. That's the surface area of a sphere. Not far off. So if the sphere has radius r, the volume is 4/3 pi r cubed. It so happens that the derivative of that with respect to r, the surface area, is 4 pi r squared. Which is kind of neat, by the way, because you know that the area of a circle is pi r squared. What's the circumference of a circle? Circumference is what? It's 2 pi r. So if you differentiate the area of a circle, you get the circumference. If you differentiate the volume of a sphere, you get the surface area. The sphere and the circle are very special in the sense that if you try to do this for almost any other shape, it's not going to work. Yeah, square doesn't work. I mean, if we did, so like here, it's the area is x squared, right? Differentiate, you get 2x. What's the perimeter? 4x, yeah. So yeah, it's something about these pesky corners ruins it. You know, corners don't play nice with differentiation, but there's no corner on a circle, right? Okay, so getting back to here, we have dv dt equals 1/3 pi times 2r dr dt plus r squared dh dt. So I think what I should have done, because we were kind of short on time, I need to change the problem statement a little bit. If we assume, instead of assuming the balloon maintains its shape, let me cross that out and replace it with something a little bit easier. If we assume that the balloon has, let's say, dH dt equal to 0.2 feet per second. All right, so suppose I'm actually just given the rate at which the height of the balloon is changing, all right? If I give you that, then if you look at this, we can relate the rates, because I'm told that they're blowing air into it at 1 cubic foot per second. So dV dt is given to be 1, all right? So like this is given, this is 1. And then we got pi over 3. 6 inches. If I'm going to use feet, I need to convert inches to feet. 6 inches, how many feet? Half a foot, right? 12 inches in a foot. So 6 inches is 0.5 feet. So 2 times 0.5 is, this is just 1. 2 times 6 is 12 inches. This is just 1. The RDT, that's what I'm trying to figure out. And then what's R squared? Well, R was, 6 inches, so that's 0.5 feet squared. And then what was dH dt? Well, I gave it to us. It was 0.2 feet per second, right? So I'm writing this equation using feet and seconds, all right? Now that you have all that, you can solve for dr dt and answer the question, right? So this is how related rates problems are solved. We try to find an equation which describes how the physical quantities are related. We differentiate the equation and then use the given data to relate the rates. I'll do more of these Friday. I know you need to see more. And I'll warn you before I forget, since I have your homework open, you do need law of cosines to do problem 97. So like problem 97, you need log cosines. But anyway, I'll stop there for today. Thanks, guys.